this video is to help with number 2 on the quiz. It's a problem very similar to one that we have done before. Just going to highlight a few things as we're going on, and one thing that is a little different, but actually not different at all. In this problem, we have this is like a box being pushed across the floor, or some object being pushed across the floor, like pushing, I think, like the Pokemon card problem from the test. Just kind of sliding something across, and you're pushing at a force that is a downward angle of 30 degrees there. Okay, I've already started the force diagram. We know that force gravity goes down, force normal is up, and it should be bigger than force of gravity because force push is also pushing down, and we have force friction. Now, in previous problems, I've regularly been giving you force friction. In this case, it is not given to you, but you are given the mu value of the surface and the object. We know that the force of gravity, or weight, is 19.6, and it says the object is actually already moving at the very beginning. Now, I could ask for a couple things in this problem. I could ask for what is the final kinetic energy and what is the final speed. Those are technically sort of the same thing, so we'll show you at the end kind of how it differs if I'm wanting to find one versus wanting to find the other. So how do I begin this problem? We are trying to find the final kinetic energy here. So what we're going to do is we're going to start with the work net kinetic energy theorem. And how we do this is we expand this side. To expand this side, I look at all the forces over here. I'm just going to go around in a circle starting at normal, and I'm going to write a work for each of them. Again, work and force are not the same thing. I call this push, by the way, so whatever you want to call it there. Then, after we've done that, so we've just expanded that side, let's expand the other. The side always expands the same into kf minus ki. At this point in time, I do start to cancel stuff that cancels. Oftentimes over here, one of the kinetic energies will cancel because it either starts at 0 or ends at 0. I don't believe that's the case here, so we're not canceling either of those. Works, of course, cancel because of the individual, write the wrong equation, that's not going to help us. The individual equation for this, and specifically you're looking at the angle right here. So as I look at this right here, I can actually see that work of normal is going to cancel, and work of gravity is going to cancel because both of them are 90 degrees to the displacement of 3 meters. Now, as I'm doing this, actually, I just realized that I think the quiz has you do these in individual. I think you're asked to find all of the works individually, which is completely fine. We're going to do the exact same thing in this particular method. This is just kind of like setting it up for the very end. So what we are going to do now is we're going to take this and use this equation. Sorry, you didn't see what I pointed at there. The work of push, use that individual equation and fill that individual equation in. Of course, you will have already done this on, I think it's part A or B, so you can just plug the number in there instead because you already know what it is. Okay, so this is essentially whatever part that is for finding work of push. Now, I think on your problem, the object is going up, so I will just give you a hint and say one of the two of these does not cancel in that particular case, and you just have to be wary of that angle. But continuing this problem, I'm going to get that equation right here, plus force friction times displacement times cosine theta of friction. And now I'm going to expand out these two over here on the right side as well, usually. Okay, so either I could write 1/2 mvf squared minus 1/2 mvi squared, or I could write this, kf minus that. What's the difference? What the heck are you trying to find? Okay, if you're just trying to find kinetic energy final, let's go ahead and leave that just as kf. If you're actually trying to find the speed, all right, then you go here. Since I believe the problem on the test has you try to find kf, that's what we're going to leave with. Arguably, it's actually just a little bit easier. So from this point, I'm going to see that the angle for friction is 180 because it's from the displacement to the force, which is 180 degrees. Okay, the angle for the push is actually nicely already given to us at 30. I don't think that is the case for yours on the test. I don't think that angle is quite as nice because that's just not the one that's typically given to you. So let's say, for example, this problem had given us a dumb angle and us that that force is actually 60 degrees from here. Well, then you just have to go, okay, well, if that's 60 degrees, then from here to here must be 30 degrees. And yeah, you plug in 30 over here in that particular case. So force of push is just 30.8 newtons times the displacement, 3 meters, times the cosine of 30 degrees. And I've already calculated this, so this is about 80 joules, positive 80 joules. Makes sense, it's adding energy in. This is like, I think part, I can't remember, I believe it's A on yours, okay? Over here on this next one, plus force friction, which is, let's see, oh, we haven't found it. So, we need to go find force friction. How are we going to do that? Just the way we always used to. We got to sum the forces. So this is just, of course, a little bit of a rehash, a reminder of stuff that we did last chapter. I'm going to go ahead and sum the forces in the y equals mass times acceleration. Remind myself about all that vector stuff because we haven't been messing around with it. The acceleration is in the y. Sum of forces should be force normal minus force gravity minus force push in the y is equal to 0. Then we would get force normal by some basic algebra here, just adding these two on the other side. And plugging in here, we get 19.6 plus 30.8 newtons sine of 30, and you end up with 35 newtons. Of course, with that force normal, we go get force friction, 0.6 times 35 newtons, and you end up with 21 newtons. Now, typically in the sum of forces, we would then continue on to sum of forces, but we don't need to. The main reason we were doing this was to go get friction. So let's come back up here. Force friction, position kind of correctly here. Force friction is 21 newtons times 3 meters times that -1. So that's going to end up as negative 63 joules. And that's all equal to kF minus 1/2 mass VI squared. Oops, sorry, we should actually plug numbers in here. Move it over just a little bit. I don't believe we have mass, but as always, we can go get mass. Mass is equal to force of gravity divided by g, which is 19.6 newtons, divided by g, which is 2 kilograms. So times 2 kilograms times 3 meters per second squared. So this is equal to kF minus 9 joules. So if I do all this work out, hey, you'll notice this is the work of the push. This is the work of friction. This is the kinetic energy initial. I just rearrange this around by adding 9 to the other side, and I'm going to actually kind of just do this individually first, so I want to talk about it. I know you don't have to do your math well, but that's what, 17, so the answer is 26 joules. And if you really wanted to find the speed from this point, you could of course set that equal to 1/2 mass VF squared. And if I'm not mistaken, you'll find that that is about 5.04. That might be a little bit off. I didn't calculate that one specifically. But going back to this real quick, why did I do it like this? Well, to understand a little bit better. Here's what this says. Hey, I started with 9 joules. The push added 80 joules of work. While that was going on, friction took away 63 joules. So in total, I added 17. So if I add 17 to the 9, then our final kinetic energy should be 26 joules, which means we should be going 5.04 meters per second, about 2.04 meters per second faster than the original. Hopefully that helps.